These notes are going to cover measurement and more specifically uncertainty in our measurement and being as precise and accurate as possible. We are also going to look for significant figures and what a number really means or how precise a number is that you see. So when we measure things, we use various implements. So say if we're going to measure length, we look at measuring with rulers, meter sticks. Sometimes we just use our own feet if we don't need to be too precise. So what we're looking at is the uncertainty there. Obviously, if you're just using your feet, literally the feet on the bottoms of your legs, and you're trying to mark across the room, you can get a good idea of the size of the room, but you're not certain exactly that this is, precisely 20 feet wide. It's 20 of your feet wide, but it may not be exactly 20 feet wide the way we look at it. So uncertainty is it's a limit to the precision of the reading, and then it's decreases the more precise you get. So changing the measurement device from your feet to say a ruler or a yardstick or even a tape measure, we are going to decrease the uncertainty because we are getting a device that is more and more precise. That's where significant figures come into play. So significant figures are digits we know for sure this is exactly what that number is, and then we're able to estimate one decimal place, and we'll get into that a little bit more in a minute. So here are some examples. This arrow is pointing to the exact same spot on each of these markings. So in all three diagrams, we know that we are between 6 and 7 units in this length. Our ability to estimate reasonably is varied based off of how far apart the spacings are on these measuring devices. So the top measurement is the most precise. And why? I'm going to zoom in. So careful, the screen's going to move quickly. So if we zoom in on this, we can see that in between this space, we can mark out 2, 3, 4, 5, 6, 7, 8, 9, 10. We can get about 10 markings that are roughly evenly spaced, and we can see that this might be somewhere, around 8 or 6. This is 1, 2, 3, 4, 5, 6, 7, 8. 6.83 or 84. We can tell we have a good ability to estimate that spot. Screen's moving again. Here, it's a little harder to tell the difference. We could probably only get about 4 or 5 markings in between there, so we're kind of jumping by 2s. So instead of 6.83, here we're saying 6.84. And then this last one is pretty tiny, and really you're only good at telling, is it on the 8, halfway through, or on the 9. And so this one I would probably estimate this as 6.85. I know for sure that it is 6 and 8 because here's the 6, here's the 0.8, and I get to estimate one last spot, which on this one I can only do by, is it the 8 halfway between or the 7, or I'm sorry, the 9. Here we have them all listed, and again the top one is the most precise because there's a lot of space and we can get quite a few markings in between there. The one on the bottom left is a little less precise, so it's a little more uncertain, or the uncertainty is a little higher. And then this last one on the bottom right is the least precise, or it has the most uncertainty. Okay, so significant figures. This is where it gets a little tricky. Definitely mark these notes. You're going to want to come back to them. I have a handout for you that you'll be able to download into Notability and work through that. So significant figures are those numbers that tell us for sure what this number is. So like I showed you earlier on that scale, we had a 6. We knew that this was an 8 for sure because the line was after it. The arrow was pointing over here before we got to the 9. So we knew it was 6.8. It was that last number that we were guessing, we were trying to figure out. So we have a few guidelines that we use in chemistry and really in all science and math classes when you get to higher levels that tell us these are the significant figures. All right, so let's kind of go through the rules of significant figures. So every non-zero is significant. 1, 2, 3, 4, 5, 6, 7, 8, 9. The zeros that are in the middle, that are what I like to call sandwiched, those are important. If this one over here is important, it means this is important, this is important. Any other number that comes in front of it would be important. The zeros at the ends are the ones that we have to kind of play with and figure it out. So if it's at the end of a decimal place, so this one here is at the end of a decimal place, it's important. Since that one is important, same as our sandwich rule above, that becomes important and that one becomes important. This is a 9, so it's already important. That's how we get 4. A way I like to think about this is if, so we'll put 90.00 up here. If you cover up that 0 and the number still reads, still has the same amount to it, that 0 was placed there for a reason. So if I cover this 0 up, that number is still 90. I haven't changed that. So the 9000, this 0 is important. It was placed there for a reason. It's significant. Times when zeros are not important are when they are what we call placeholders. So taking that same 90, okay, if I cover this 0 up, it no longer says 90, it says 9. So the job of this 0 is just to hold a place, to make sure that 9 stays in the tens column. So it's not important. Its job is to hold the place, not to be important. So if we're kind of looking down here, we can cover up, say, this 0 and this 0. Well, 0.23 is different than 0.0023. So these two are not significant, just the 2, 3. Again, for the 900, if we cover those up, it now just says 9. So those zeros were placeholders, they don't count. Okay, so when we're looking at significant figures and we start to do calculations, there are some specific rules depending on what kind of calculations you're doing. And here are the rules for addition and subtraction. So really, you just add and subtract like normal. At the end, you round the answer to the same decimal place as your least precise. Now, it's really the placeholder of your least precise. So here are some examples. We have 12.3, 12, and 12.34. Well, the first one goes to the ones place, or the tens place. Sorry. This goes to the tens, this goes to the ones, our second one, and this one goes to the hundreds place. So when we add them up in our calculator, we're going to get an answer of 36.64. Well, we don't know what the places are for 12. Maybe this was 12.13 and it was rounded to 12. Well, 12.13 would not add up to 36.64. Or maybe this one over here was 12.34 that was rounded down to 12.3. Well, again, that would not add up to 36.64. So 36.64 is not the real true answer that this could be. We have more uncertainty in there. So we take our answer to the one that we are the most certain about. So the least precise one we have is this one here. It's only precise to the ones place. It doesn't have any decimals. So we need to take our answer to the ones place. And that's why we go with 37. If we look at this other example that we have 100.24 minus 90.345 minus 2.5678 equals 7.3272. And again, we are not sure of these last couple of places because we don't know what comes after this 4 or what comes after this 5. So we have to go to the least precise, and the least precise in this group is the 100.24. So since this one is precise to the hundredths place, we're going to be precise to the hundredths place in our answer. Multiplication and division, I feel, is a little easier of the two types of calculations. So you multiply and divide like normal, and then at the end you just round to the total number of sig figs for your least one. So here we have 2 sig figs, 4 sig figs. So when we do our answer, this is what the answer comes out to, but you round to your least number of sig figs, well, 2. This one had 2, so this one has 2. Down here, if we look at 51.00, that has 4. 3.0 has 2, so our answer has 2. Like I said, these I feel are easier to do, and luckily that's the majority of our calculations will be Okay, conversion factors. When you have anything that is a constant, so every time you have 1 meter, it is 0.001 kilometers. Or if you have 1 kilometer, it's 1,000 meters. Every single time. These are a constant. It's exactly what it's going to be. We don't even look at these when we do significant figures. So if I said you had 5 kilometers, how many meters? You would take 5 times 1,000 equals 5,000. You would round this to where it would only have one significant figure because your original only had one significant figure, and we don't care about the 1,000 since it is a constant. So like I said before, and I'll reiterate these take practice. It takes repetition for you to understand this. That's why we're going to work through these and take some extra time with them, but it is a good skill to have.